Kyle Smith, and this will be my Physics 2 lab final presentation. All right, so there's a bunch of objectives that we've had to hit for this class. And so basically what I did is for each objective, copy and paste what the requirements were on the syllabus, and then I just copy and pasted from my lab notebook where I thought it was good evidence that showed. There are parts where I use the same evidence to show the two different learning outcomes, but I feel like they both shows equally well the learning outcomes. So this first objective was collect the data and revise the experimental procedure. Um, and so this is kind of like my bread and butter, honestly. During the course of the semester, I was mainly the person doing this. So I had a lot of examples showing independent, dependent, listing those out. And so here shown up above are three different examples. Uh, and so basically in this like section where I have to show this, it's asking which variables to control and how to control them. And so in this example to the left, uh, I was choosing the the diameter and the materials and the range and holding the other two constant while changing one, and that's how you isolate a specific independent variable by treating everything else as dependent. And so that was kind of the technique I did on that one. For the second one, I went over the dependent and independent variables. Again, just figuring out what I need to hold constant, what I need to change. You know, that's the main part that we were learning in this lab is just pretty much figuring out what we're trying to figure out and figuring out how we can set up our experiment in a way that makes that possible. And the first step is to do the independent dependent variable. Um, and so yeah, this third example, again, independent and dependent variables very important. Um, and so I also listed out which variables to measure as well. Um, you can see on the examples that I gave, uh, choosing the different types of variables is, like I mentioned, how we figure out what it is. So deciding how to measure data was very important for this lab. We wanted to get enough data to support our conclusions. You know, you just don't want to just show up with just one piece of data, no means, no nothing. And so right here on the left, it was the light diffraction lab. Um, and basically, I made sure that we did enough data tests per sugar solution to get enough variability. And it just depended on, the lab, but the key standard that I always shot for was at least three trials per whatever, even if it was 20 different things, three trials per that 20. Um, it ended up being a lot of different permutations that I feel like was enough to, generate meaningful data. And so yeah, I discussed that here on the right as well, choosing the amount of trials per turn, um, per length, per current, um, while isolating the other two. That kind of goes back with the other example of the independent and dependent. These two work well together, I think. Um, and so as long as you had enough trials, you can just avoid the uncertainty that came with having not enough trials. So there was one lab where using the predictions actually was very important. So it was the RC charging lab, where we figured out the curves of how long it took to discharge and stuff like that. But here, using prior knowledge, knowing like, all right, this is the formula for it, I was able to figure out a theoretical calculation for it. And the good thing about theoretical calculation is that it keeps you in the ballpark of what you're trying to show. And I know it takes away the discovery aspect because you're showing something that's already been discovered, but like having it is definitely a good like guide, hold your hand type thing that helps you have a direction when you're doing these projects. And so anytime I would do my calculations in Excel, um, I remember it was for it was not this capacitor lab, but there was another one, um, where we were di discussing the formula for it. It was the like area over length or whatever, um, that formula. And so figuring out the theoretical from that was quite easy. And so that's what I did for that. And it made the our calculations easier on our end when we were checking it because if it was off, then we did something off on our end. That's what that meant. So doing these theoretical predictions was a good way of checking our work. Um, and also doing like dimensional analysis on answers as well, figuring out like, all right, if we use the voltmeter, for example, and set it to the, I don't know, the milli range, then we want our answers to be correspondingly within that milli range as well. We wouldn't want something in like the kilo range when we had stuff in the milli range, you know. So just being cognizant and aware of our different variables, the units of measurement for those, and that we were generally fine because like what we collected generally held, but it was good to still check it anyway. All right, so the next thing I need to show is using the predictions about the expected data, certainties, and schematics to consider the spacing and frequency of the data, quantify systematics or design tests to quantify it, and identify where the main effect might be. Um, so I gave two examples. The first example was in our lab too, using a multimeter. Uh, and so basically, I identified where the main effect might be, um, talking about generally the readings of the multimeter and what those effects mainly are. And then on the left, we it was a magnetic field lab, and this was at the end, and I was like reflecting on it, but I considered where the main effect might be and what we're trying to show, and using prior knowledge, using the formula, I identified, well, there's three basic variables, and this is where the main effect might be, and that's exactly what we were doing in that lab, holding things constant, changing the other things. And that's how we quantified their schematics uh, and designed the tests based on this whole idea is knowing what to hold constant, what to change, based on what the main effect might be, and you just kind of just go from there, try to figure it out, trying to do it on your own, and uh, figure out what that main effect is from the data. Kind of cool, honestly. So the second objective is kind of like what you think of doing an experiment is the actual experiment itself is collecting the data, recording it. So objective two is evaluating the processes and outcomes of an experiment. And so we were supposed to analyze data using computational methods. I just use Excel through the year. Maybe somebody used MATLAB, Python. Shout out them if they did. But so yeah, I had a lot of examples. I did the calculations quite a lot. Like when I will reflect on it later. Um, but I was kind of that data guy for the first half of the semester, and so I had a lot of evidence to show. Uh, and this graph on the left was one of my favorites. That was from when we were doing the electric field lines of object or whatever, or paper, and that was the graphical representation of it. And I just liked how detailed, how uniform everything was, how everything ended up coming out good. That's why I kind of did the data collection and stuff like that. Just because I just like seeing how everything came about, how the graphs formed, and how that affected the ratios of whatever we were testing for. Like like knowing that something was inversely proportional to its length, for example, uh, and then checking that with the graph, um, like for our middle one, remember that capacitance stuff I mentioned earlier. So um, we were testing it versus area and distance, and so capacitance is A over L, and so we want to see a proportional relationship, and we see that that's the tiny graph on the left, graph the capacitance versus area, and we see a linear uh, proportion um, going up, and then capacitance versus distance would be C proportional to 1 over length. And we see that there, where it's proportional to 1 over, and it's a curve going down like that. And so, kind of verified it based on like my math knowledge or whatever. But yeah, just recording it and putting it in the data and knowing how to create graphs was important too. So a big part of this class was deciding how to analyze the quality of our measurements. So identifying and distinguishing possible sources of uncertainty, either from the measurement model or the physical model, distinguishing instrumental uncertainty from random uncertainty, uh, and then determining how to quantify these sources of uncertainty and propagating the measurements of uncertainty through calculations. And so we hit that, especially in this index or in this refraction lab with the sugar water solutions. Having a standard error on that was very important, the standard deviation, because you know the collection on that you can see from the graph was not, you know, what we thought it would be. And so having the little whisker bars definitely gave us more confidence that, you know, there is some variation in this and that like our data is more normal than we think it is. And so we found anytime we did like anything with multiple trials, we would always gather a mean, and then you know, we would do like an implicit standard deviation check, you know, checking for outliers and things of that nature, just making sure that our data aligned with, you know, what we kind of determined and the previous, what we've discussed previously with our unit of measurements checks, but also aligning with, you know, generally within our mean, a couple standard deviations within our mean. You don't want to go outside that. That means we did something wrong or well, the way we're collecting is wrong. Anytime that happened, we would always get one of the LAs to come and tell us like, yo, what are we doing wrong? So it was a really good way of figuring out like, yo, like maybe we're heading in the wrong direction in this lab. But yeah, that showed some of our mean calculations and also those whisker bars to show this section. The next section that I'm supposed to talk about is comparing data to a model quantitatively. And so plotting data and modeling it on like a traditional XY plot, linearizing data, performing linear and nonlinear weighted least square fits. I didn't do that. Plotting residuals. Yeah, I don't think we got that in depth with our statistics. It was just mainly standard deviations and means and linear graphs and stuff like that. Plotting the data as collected, and then evaluating methods and data, checking uncertainty, you know, going along as we do the experiment and just monitoring stuff and making sure that we're on the right track. And so you can see here, this was that magnetic field lab. And so these are the graphs. And so for each graph, it's one thing that would change versus everything else being constant. And so that way we can have a nice one-to-one graph that we can just graph and show the relationship there. And that's kind of how you figure out what the formulas are. What you see, if you see a graph going up, probably in the numerator. If you see it going down, it's probably in the denominator. So that's a good way of thinking about it. Um, and so yeah, I mean, that was just literally every single lab, just graphing something, and from that graph, looking at it and then figuring out like, yo, this is the formula. And so um, on the left, this is me interpreting our data. I'm in orange. So our predicted values were off compared to our actual values because we did not consider the value of what the K is for the paper. And so I went into um, like why it was off, why it wasn't matching up with our theoretical values that I calculated some in the first section. And so just having these graphs is honestly the most exciting part of this class. Just generating these and looking at them and seeing that what we're actually doing is real and it's not just made up. So yeah, I think that's good for this. So the third objective is extending the scope of an investigation. So when our data and results do not come out as expected, determining plausible explanations for the disagreement, test whether the results are repeatable or reproducible, check whether results are repeatable with improved precision, isolate and test components of the system, and design new experiments to test. And so like on that last slide with that reflection, uh, I was I determined the plausible explanation for the disagreement. And so in that lab, we actually didn't check for the dielectric constant itself. And so the dielectric constant itself would affect the measurements, and therefore our values were always within that ratio of the dielectric constant off. And so we were able to be like, yo, we're actually good. This lab. And then, like I said previously, uh, isolating and testing components of the system, like troubleshooting, but instead of like doing it like all at once, we would like as we go do it. So we were kind of more efficient with it. But like figuring out like what's off here, what's wrong here. Like there was this one lab um where it was we were doing the uh the light the light detection lab, the double slit experiment lab. And we were measuring our n values incorrectly, and so our results had a very wide, very n value, and we were confused on it. So we asked, like, actually, you actually helped us out um, with it, and and from our results, we were like able to figure out the reason why there was that disagreement, and then refine our our experiment to model that new criticism. So here's some pictures showing some of that. And so in this lab, we're using a multimeter to sketch electric field lines. And so at first we were just like bumbling around, just like putting it wherever. And we're like, how do we do this? What the heck? But then we're actually shown how to do it, and it was like more systematic, one after the other. Um, and so like just being aware of like what your data is looking like, and uh, being able to go back in and redo it is important. Like we didn't just stop and be like, oh, well, our data's bad, so we just move on. Like, we didn't do that. Like we went back into it. And then the grid of numbers on the left was the more systematic approach. Uh, that was when we like got in and graphed every bit. But on the paper, like we started to check at every spot and make sure that the lines are actually following what it was. All right, so objective four is communicate the process and outcomes of the experiment. So this is describing the experimental goals, the justification for all decision made, supplementing when changes were made, using previous notes in the lab notebook to inform the design of future experiments, explain the experiment broader context and uniqueness of investigation, present conclusions, claims, and outcomes. And so that evidence I mentioned earlier, uh, I used it again here because I thought that this was a good conclusionary type statement talking about the lab and its general nature. And so I kind of just used my notes in the lab notebook to to show that conclusion of deriving the three basic variables, uh, and then using our evidence to show that as well. Like I mentioned, the proportionalities, the figuring out what is proportional to what, how it looks, kind of figure out our equation from there. And so putting that all together is kind of how you did that like that. All right, and then objective five was just talking about conducting an experiment collaboratively and ethically. Uh, just don't be like a jerk, don't take one spot uh, and then be like, y'all do something else. I don't care. Not being the leader every time, divvying up responsibilities, going with the flow, letting other people take charge even if it's slower, that kind of thing. Just being patient with this whole process. And so I did a reflection. We actually made sure to rotate the people like we discussed it, like especially after that midterm, because it was kind of like a wake up call, if you want to call that, about how we were doing things. Like I was just dogmatically being the data collector and the lab setup person, where figuring out the variables, and that has its merits, but also setting up the lab and being more that liaison type person also helps as well. And so getting to experience the other types of roles as well. And that definitely helped me internalize more of what we were learning. I will say, like, uh, setting up the lab helped me remember the lab more. I will say, like, there were some labs where just doing the data was monotonous and I wanted to block it out of my head immediately after. Like that one lab where we had to like collect like it was like 100 data points. So I was like gonna tear my freaking eyes out doing it at the end, but kept through it, and it paid off. You know, we got that cool little graph, but like definitely didn't enjoy that as much as if I were the one, touching it or doing something else. I don't know, but yeah, after the midterm, we started sharing the roles more, and it ended up pretty good. So I guess the grade I want to propose is an A. Um, I only missed one lab class, showed up to pretty much all of them, and when we did it, we did it. We made sure that we got the right result. Check with LAs, just making sure that what we were doing was correct, uh, and having fun with it. Because like ain't no point in learning something if you're not gonna. So yeah, this is my final presentation for the lab. Thank you.